There's a sense that engineering is all about math and science. Some people say engineering is applied science. And certainly the math-science death march of the first 2 years of engineering education is profoundly misleading. By emphasizing math and science to the exclusion of other modeling modes, we imply in an engineering education that the only meaningful models that we use in engineering are those that come from math and physics. And so what happens is that young engineers become confused on their first jobs or their first real-world assignments because they don't know how to use appropriate models to the task at hand. And worse, they don't think that what they're doing is real engineering because they're not using those math models that they learned in engineering class. So our purpose here in this micro lecture is to better understand the types and breadth of engineering modeling so that we can be better engineers. So how are we going to do that? Well, we're going to examine what is a model. We're going to talk about Newton's legacy, and we're going to talk about equations versus words and images. We'll then talk about matching models to problems appropriately and how we might do that. Ask what models are used for. Talk about how the best engineers, the ones who create whole new categories of product and service, are broad spectrum models. We're going to take some results from philosophy and take a model of arguments as a unifying approach to engineering modeling. And then we're going to return to our tortilla problem and talk about flower physics another time here. So what is a model? A model is a system that represents one or more facets of some other system. And so there are many combinations of model and the facets that are modeled by that model. For example, a drawing or solid model is looking at the geometry of some object. A prototype, a physical prototype, is looking at the geometry and the functional operation of that device. A graph is plotting the variation of one variable with some other variable in time or space, for example. An equilibrium equation is looking at select steady state as state variables at steady state. Dynamic equation is looking at their variation, and a computer simulation is similar to different kinds of equations in that it can calculate those on a computer numerically. So there are lots of different choices for us available when we talk about a model, but the point is that we're representing one or more facets of some other system when we do modeling. Now, models capture what we know, and the study of knowledge is what we call epistemology in philosophy. The study of the existence of things is sometimes called metaphysics or ontology. But it's not the usual case that we investigate what engineers know and how they know it, but there's been a movement over the last 10, 20 years to consider what engineers know and how they know it. And here I've got Walter Vincenti's wonderful book that examines that through a historical lens in aeronautical engineering case histories. And Dr. Vincenti makes the point that engineering knowledge is distinct from scientific and mathematical knowledge in very important ways that we need to think about and reflect on more specifically. Now, Newton invented the calculus at the same time Leibniz did and published his world-changing, life-changing book in 1687. At the time, it was remarkable the amount of agreement between Newton's equations and the predictions of planetary motion and the measurements of planetary motion. It was astounding, and rightly, those equations changed the world. Of course, today in engineering, we learn those in those equations in statics and dynamics and use them routinely. And Newton's accomplishment was enormous. And ever since, this model of knowledge has sort of set the gold standard for what constitutes knowledge, in the sense that it's remarkably predictive and and represents the real world with remarkable accuracy. Now, of course, as a result, these models were accorded high status, and one of the questions we want to ask here is whether that high status is synonymous with efficacy, and we want to actually question that and be a little bit more critical of that connection than engineering has been in the past. So Newton-style models dominate engineering problem solving, but the point is that engineers often maybe more frequently use natural language and other forms of modeling in engineering practice. So many first models are verbal. Single word or noun phrases, description of objects, feature lists, dimension lists, engineering specs, standards, or claims. So there are lots of ways in which we model things with words in engineering, but we almost never talk about those things as models, but they're certainly important. Moreover, many engineering models are images, visual representations of different facets of this system or that system. And Eugene Ferguson's book, Engineering in the Mind's Eye, discusses how that was once widely understood and widely practiced, but it's become devalued after the Cold War. Ferguson argues, and I agree with him, that was and continues to be an educational mistake. But the point here is that many engineering models are visual representations of the facets of some system. Now, we've been following along with the back of the napkin, and there the effort is to make all of our models, or to oftentimes use visual modeling as a way in to getting our conceptual understanding concrete. And so here we just want to emphasize that diagrams, as in the back of the napkin, can be models, and they actually are an interesting link between visual representations and conceptual or verbal representations. But none of this really suggests how it is that we can match models to problems. What characterizes an appropriate model in engineering? And if you're in class, you might take out a piece of paper and write down 3 attributes that you think contribute to a model being a good model. And take a couple of minutes to do that, and the instructor can pause the tape and give you time. If you're watching this straight in, we'll just continue on. Now, one of the things that we want to think about is that engineering is always performed in a context of limited resources. And that's without question. I mean, it's never the case that an engineer is given a job with an unlimited budget or an unlimited number of people to perform the task at hand. We're always in a limited resource environment. So that suggests that there's kind of an economy that surrounds engineering always. Now, when we think about engineering, another dimension of an engineering model might be its accuracy or its predictive capability. So that gives us at least 2 dimensions that we need to consider when we think about a model. A model can be more or less accurate. It can have higher or lower costs. And so here we want to just explicitly discuss the economics of modeling. And again, recognize that an engineer is always doing whatever he or she does in a context of a limited available resources. So when we think about this, we can think of there being a spectrum of models, from models with fairly low costs and high relative predictive accuracy, or high error, to fairly high cost models with fairly low error or fairly high predictive accuracy. Now, here I've labeled this graph that the engineers are going to tend to live at the left at relatively low costs. Engineers are inventors, and the scientists or mathematicians are actually in the business of creating new, better models. So they're at the frontier of creating new models, and oftentimes those models are in some sense more costly or complex.